So we are really delighted to have David here speaking to us about the capabilities of modern AI with some examples of how this can be applied. So please give a very warm welcome to David.
Thanks so much. Great to be back in this room. I was just saying to Kaz, the last time I was here, it was a senior management team from Tencent, sort of fishing for intellectual property with the AI profs at the university. So the kind of stuff that I do is very similar but different to that which you've heard about previously. So I do machine learning in healthcare applications, but not imaging, because that's very well populated. There's a lot of tremendously talented people who do imaging, CTs, MRIs, ultrasound, X-rays, and there are some good technologies that underpin those, CNNs, UNETs, etc. But I do everything else. So if it's not an image, that's probably what I do. It's things from omics all the way up to text and public health, all the way down to individual care in hospitals or at the home. So I thought I'd use this opportunity to give you a bird's eye view of the kind of things that AI can do for you, and coming from a particular perspective as I've just described. So in my field, one of my occupational hazards is that I have to listen to a lot of people talking about AI. And it's often at two ends of a spectrum. Now, at one end of the spectrum, AI means this, drawing lines through plots, or the little multi-layer perceptron at the bottom, proposed in late 1960s, early 70s. And I have to say, there's a certain maturity and whiteness and maleness about the kind of chaps I usually have to listen to, they're usually chaps, might be close to retirement, telling me all about machine learning as it was in the 1980s and 1990s, and which they still think is relevant. At the other end of the spectrum, we have Coat Pope. So if you know Mid-Journey 5's Balenciaga Pope, so the Pope doesn't wear Balenciaga, but if he did, Mid-Journey 5 has captured it quite well, and so you can see it does the hands pretty realistically now, which is was the real problem with Mid-Journey 4, and also ChatGPT. So this is at the other end of the spectrum where we have a lot of people opining on these. And often from the point of view of what they've read in The Economist or The New York Times, nothing wrong with that at all. I like those periodicals myself. But there's a gap, isn't there, between massive generative techniques that require Microsoft scale ChatGPT, I'm talking about here, Microsoft scale, OpenAI type resources, and stuff that we've left behind from literally the 1980s. There is something that happened in between these. And really that's where I'd like to just touch on today, just to fill in some gaps, and to, I like to come from the perspective of, if I didn't know a huge amount, if I was interested in filling in this gap between here, what would I really like to know? So that's my goal for today. Okay, so the way most, as I said, I do a lot of medical work. Probably 90% of my projects are in medical science, which is very rewarding. But again, another occupational hazard is I have to read a lot of papers and proposals that are to do with machine learning, and I use the word machine learning here rather than AI. My friend in Microsoft says it's machine learning when you talk to scientists, and it's AI when you want to sell it. And ChatGPT is good old-fashioned machine learning. It is actually machine learning, right? So there are some things which are not machine learning which can still be called AI, but they're few and far between. So when most people say they're doing AI, they usually mean this. They usually mean get data set, build model from data set, and use it to predict something. So cancer, not cancer, realistic picture of Pope wearing Balenciaga or not, etc. So, and there's nothing wrong with this. You can you can certainly pick a lot of the so-called low-hanging fruit with this kind of method, and that's what you see in the medical literature in my field. Pick up the Lancet, the New England Journal of Medicine, the good stuff. If it's describing machine learning, 99% of the time it's talking about this. Why is that? What's wrong with this? Is there anything wrong with this? It's get data, build model, predict fixed classes. Okay, so what I mean here is, in terms of the data, just on the left-hand side, apologies. So I'd have rows perhaps as examples. So those could be perhaps patients. And then columns might be, for example, In the non-imaging domain, these would be things I've measured about the patient, perhaps their omics. There might be billions of columns. If it's imaging, then you haven't got columns, you've got a matrix or a volume, of course. But the idea is the same. And you would be surprised just how much this happens. The reason this happens is because in the medical field, and certainly in many other fields, the comparator, the orthodoxy, is to do this technique. And the field of medical statistics is a very well-advanced and erudite orthodoxy by which medical science rejects crazy things. It's a very healthy orthodoxy. And my wife's a medical statistician, and I built my lab after the late, great Professor Doug Altman, and David Cox is one of my heroes. In fact, I inherited his library, funny enough. So I do love me a medical statistician. And a medical statistician would do it this way. Get data, build model, predict classes. And that's good because you can show that your device isn't killing people. It's great because you can show your drug works and all the things that you need to do to get FDA approval and to make sure it scales up. But, something's coming, right? So what happens if you want to do something slightly different? What happens if it's not cancer you're going to predict, but it's now severity or remission or something else? Some other quirk using the same data set. It's time to build a new model. In those examples, you cannot repurpose your existing model. You've got to turn the handle again. No big deal if that's a medical statistical approach. It's literally 2 lines of Python, boom, done, retrain in 30 seconds. If it's something more crispy, like ChatGPT, that's a 6-month process. I found it very amusing in ChatGPT 3.5 paper, which is the last paper, ChatGPT version that actually had a paper associated with it, snort, because it hit OpenAI. In that process, they identified that there were bugs in the input set, and they said, we couldn't fix these bugs because that would mean retraining it, and we didn't have another 6 months. So there we go. There were problems, we know about them, but we can't fix them because it takes too long to train. So the idea here is that retraining a model is often very expensive and you don't want to do it. What happens if you've got really different classes? You've got a totally different or a data set from another hospital. A validation set, as might be called in the medical terminology, or just some extra held out test data that you didn't consider previously, which has got a slightly different view, or et cetera, et cetera. Okay, so conventional models mean you are rebuilding those things every single time. And that's not great. What can modern machine learning do for you outside or even inside the medical imaging domain these days? Okay, so we can cope with time-varying data very nicely indeed. And this is something that machine learning is very, very good at. It is definitely still the case. It's been the case for a long time that the best hedge funds, a lot of meteorology, a lot of cases where you need to forecast and cope with really proteinous, noisy real-world data requires machine learning. You can do this with medical statistics, and some things grew out of medical statistics, but modern machine learning is really good at it. If it changes through time, you want to be using machine learning to do this for some reasons we can touch on later. And there are certain classes of models. If you know the jargon, you know the basic workhorse is the LSTM, but there are plenty more examples of models that change through time in terms of machine learning. And in the same models, we then compact those massive input data spaces, which I described as, they could be millions of columns if you're doing omics. They could be really nasty time-varying waveform sensors, which are very noisy and artifactual. And you can boil those down and reduce them to informative summaries using a lossy compression system as part of your model. These are no longer different steps where you first of all tidy up the time series, then you construct a predictor, and then you compress and wring out the noise. In fact, this bit at the top was by David Mackay in his PhD thesis from Cambridge in about 1994 when I was still at school. I'm deeply impressed that his PhD thesis we're still using 20, 30 years later. The late David Mackay, of course, if you know him. And then from these models, within the same model, we can do phenotyping. Phenotyping is the jargon word in medical science for meaning like grouping, clustering. Can I find things about my new disease that I didn't know about before? So you're familiar with type 1, type 2 diabetes. Maybe I'm discovering type 1, type 2, type 3 asthma. Lots of modern diseases are complex. They're families of diseases, so-called. And the distinguishing parts between what makes these phenotypical groups might not be known. And this is the same in multiple other settings too. Whether it be, I'll show you my background in a minute. My background is in critical systems, jet engines, nuclear reactors, etc. There are interesting phenotypes to discover. braking slowly, braking quickly, this thing's fine, etc. These are phenotypical groups that you can discover. Within healthcare, we care about different disease classes or different people classes in the data sense because you might need different drugs. Maybe new drugs are relevant for different populations. So there's a drug discovery component to this work too. Concurrently with that, we can predict things. So we say, from these same data that I'm phenotyping this disease or this power plant, whatever it is, I can make predictions about severity. I can make predictions about what it's going to be doing next week. And I can do lots of different predictions, reusing the same model without retraining, because it's big and it's expensive. And also these things are like children, badly behaved children. If I want my child to learn, one of my two boys, poor them, to learn geometry, I'm going to teach them algebra, and I'm going to teach them some other math subjects as well. And these slightly less well-behaved systems are just like that. If you want them to make predictions given a certain type of data, show them lots of similar data types, because a lot of the complexity of these billions of parameters in these models is learning how to parse and how to ingest the data, not so much about the specific task. So, for example, genomics applications or sensor applications, a lot of the data that it cares about are just being presented with similar data from other applications. So I've got a rare disease genomics project with Professor Jenny Taylor, and you don't get many data for rare diseases by definition. But when you do get them, you get a gazillion genomic sequence data points. But what do? Well, we've actually got genomics for loads and loads and loads of other people who haven't got these rare diseases. So a lot of these models can be, in this part here, these auxiliary tasks, they can be self-supervised, they can be, you can bootstrap that process by teaching it other similar things at the same time. And so I hope I'm painting a picture here of more general purpose models. There's still the role for the human design engineer here. The devil is in the detail in putting these things together. But also, as I'll touch on later, we do need machine learning to help us do machine learning now. Okay, here's an example. So here is an example of taking a model in a complex cardiology setting using 2 million cardiology records. It's a lot of data. It's the world's biggest resource. And I won't explain the plot. The vertical axis is approximately how well you're doing. It's a C-statistic, area of the receiver operating characteristic, for those of you who know. And I'm doing a whole bunch of different tasks through time, as shown by the colors. And you can see what happens is this complex machine gets really good at the first thing it encounters in green, and then it starts to forget it, because it's being introduced to new tasks as we go through time using the same data, using the same cardiology data. So it's called catastrophic forgetting. It just remembers what you last showed it, and it forgets the stuff that you showed it recently. And within the general topic of meta-learning, which is how you get these big bad boys to behave using complex and reusing these models over complex time series, we can pull up the behavior of these things and keep them performing well through time. And the nice message is that these things perform better on most or all tasks, because like that child, they're being shown a curriculum of broad data types across multiple different tasks. And what we're not doing is a different model for a different task every time we encounter something new. Does that make sense? These things get better through reuse, and that's the key insight here. Okay, there's been some cool stuff come out of here. I won't ask you to read these. As examples, during the COVID-19 pandemic, lots of great research was done. I work with some really gung-ho, awesome medics, including Andrew Salton, who pushed us to create this thing from routine data. So what this did was a quick and dirty AI-based test, machine learning-based test, deployed in the emergency departments of 4 NHS trusts from existing data, blood test data, which all patients get every day in all hospitals in the UK. So it's routine data, it's there in the background, doesn't require any extra infrastructure or training or cost. From this existing very rich resource, can we predict who's got COVID-19, identify who's got COVID-19, predict what's going to happen to them, get ventilators ready, etc. From this routine data type. Now that's something I'm really quite keen on. If you ask medics or anyone in any industry to do more data acquisition, it's expensive, it's irritating, it requires training, they don't want to do it sometimes. I used to work with Rolls-Royce a lot, trying to get Rolls-Royce to do anything they don't normally do. isn't ever going to happen. So you can only operate the data in some settings with what you've got. And here, this was an example of doing that. So from those blood tests, can we make all those predictions? And it uses the kind of technologies that I've described so far. To touch on something I don't think we've heard about so far, it's another bit of jargon. I get 100 different investors per unit time trying to get us to do something in this area. Federated learning is a very important component of what I've described to you. Federated learning, particularly in medicine, is where you move the model between data repositories. You don't move the data around. So that's great for me. I'm no longer asking my N different NHS hospital trusts to do governance and send me data. I'm saying, can I take a model to your ED? Can I let it sit there, observing, soaking up data, training, and then can I move the model, and only the model, and demonstrably not any of your patient data, to the next hospital, please? This is the first time I think I've ever seen federated learning done in anger in practice. And this was again done in the pandemic. There's a nice couple of Lancet papers to describe this stuff. Running on a Raspberry Pi, run from the Cambridge shop just down the road from my parents, and runs in the ED and does model-to-model training in that way across sites in healthcare settings. So federated learning does have advantages in most other industries as well. You don't want to move these massive data sets around. It's okay to move the model around often. I think I'll probably skip over this one. We've made that point. So there's a whole bunch of capabilities that modern AI can do for you. And these are things that often are not considered, and I don't want to be rude to my medical imaging colleagues, but sometimes they're not considered in medical imaging either. So what happens if there's noise on the input? I deal with noisy sensors and noisy data a lot. Maybe it doesn't exist perhaps in a high quality CT scan, but in ultrasound, definitely there. In all the kind of data I've shown you so far, there's absolutely noise, and you have to cope with it in a principled manner. A good machine learning system, a bad machine learning system is like an idiot savant. It will always make a statement, no matter how unconfident it is in the answer. You're forcing it, you're obliging it to make a decision, even when it doesn't know the answer. Okay. So a good way to boost performance in any setting, but particularly in the areas that I care about in critical systems, is to choose not to make a decision if uncertainty is high. Quantify uncertainty in output. Say, I'm sorry, I don't want to make a decision. If I did, it might be this, but I don't want to make a decision. This came from a long time ago from Rolls-Royce. They said, you give me a traffic light system, red, yellow, and green from a jet engine, and that's great, but what do I do with amber? Can you just make it red or green, please? Because I either land the plane or I don't. I can't kind of land it with amber. So they didn't want confidence in the output at all. But what you can do is not show the red or green light if you're uncertain. Here's something that's very, very important and which a lot of people skip over and is becoming a key point for modern machine learning because our data sets are now enormous, often. And even if your task doesn't have an enormous data set, there are analogous massive data sets that are helping you in the background. And this isn't saying which variables are important. That is bog standard feature selection that's been around for N years. But this is saying which examples are informative. So I get asked quite a lot, how many more hospitals do you need to make your thing better? Because each hospital is going to cost us 30 million quid to get of data. And my answer to that is, the standard answer is, I don't know, more data is better. Just give me some more hospitals, please. Not a great answer, when there's dollar value attached. So if we get time, I'll show you some technologies a bit later, which rank all of your input data by informativeness. So these patients were very informative at this stage of the proceedings. These ones were informative later. If you want to improve the performance of this model, don't give me these 80% data that were largely uninformative, that aren't going to help me anymore. Give me these guys up here. Give me people from these wards, people with these diseases, and I will show you improvements. And that notion of assigning informativeness to mega data sets is something that a medic doesn't know about. Most medics these days have got a big old data set. They come to me with terabytes of X, Y, Z. But if I said, what's the level of informativeness in here? Which patients are most interesting? They're on the back foot and they're making decisions based on their med school. A big part of modern machine learning is how you train these big things. So this is called curriculum learning in the jargon. How do you build a training schedule for the thing you're striving to learn, to teach, that's doing the learning? Do you just get it to step through your billion data examples one after the other. That's what happens by default if you just turn up as a grad student to PyTorch, or whatever your favorite programming language, and try to build a box. This is totally commoditized now. My 12-year-old son is taught to do this at school, by the way, like batch gradient descent, just stepping through a data set. But when the data sets get very, very big, you cannot do that any longer optimally. And how do you get labels? So I've shown you class labels here at the end. You've got scans, cancer, non-cancer, whatever it might be. But in my game, where you've got 5 million patient examples, you probably haven't got great labels for all of those 5 million people. And if you did, well, how would you get them? Back when I was a student, in the dark ages, I'd have 100, 1,000 patients. And we could get 2 consultants or 3 consultants for the tiebreaker to label individual patient records to say, here's the thing I care about, in the time sequence, to point to that part of the stream and say, this is interesting. There's errors in that, people have got different opinions, and it certainly doesn't scale to 5, 10 million examples. How do we do phenotyping at the same time, grouping, learn something about it? And going back to Cote, can we generate synthetic data examples? This is good for sharing. In my field, I can't share data. Medical ethics prevents me from doing that sensibly. That's important. But I can share models that generate data. That's okay. So I can construct the Oxford model based on some cardiology data and share the Oxford model with people. That becomes a standard tool for people who don't have access to all of the enormous data that we have. But also there's something in it for us too. If we have data generators, we can generate data and improve the performance of our models. And this is something that my learned colleagues in medical imaging do a ton. They will augment their data set by adding noise, rotating, shifting, adding Koch signs or whatever. And it's a bit harder to do that in omics or time series data. So we can do data augmentation through those kind of generative methods as well. Okay, I want to leave some time for questions. So I probably want to accelerate and just give you that bird's eye view that I promised previously. Because we're in an AI for business environment, I thought I'd just quickly touch on the fact that these things can be big business, as I'm sure everyone in this room knows. The top 3 things I did when I was a student with my awesome supervisor, Professor Lionel Tarasenko, known to many in the room. We didn't create Rolls-Royce, but we did work with Rolls-Royce. In fact, it's got my PhD thesis work sitting on the engine of the Airbus A380, which I was on with great pride last week, just looking at the engine. And it's on the Eurofighter, which I would totally love to fly on if anyone can get me on one of those. And the bottom 2 are things we've done since. This thing was bought during the pandemic. Stress estimation from wearables, bought by HUMA, and a large company where the CEO was Lord Drayson, previous science minister, trying to do drug discovery on the one hand and NHS patient-style interventions, which is obviously my bit, on the other hand. And everyone in this room will have examples of their own as well. The kind of data that I deal with, just to give you an idea, a feeling for what's going on, time-varying data, things that vary minute by minute, hour by hour. When I started as a student, it was all on paper. We put these things into the hospitals so that we can get electronic data. So all of the OUH now uses our systems and we have ethically approved access to these data, which allows us to make good predictors from these things. I've told you about blood test data. This is the lingua franca, the very common language used by a lot of medical applications, because these exist all the time. We're getting more and more of these things: genomics, proteomics, metabolomics, particularly for cancers, but increasingly for other types of disease, and often for bugs themselves. So we have some great projects with the infectious disease people here, Derek Crook, Sarah Walker, if you know these people, Tim Pite, for being able to take bacteria out of your blood sample, same-day sequence, predict which drug is going to kill the bug. Normally that's a 2 to 4 week process if it's tuberculosis to work out which drug kills it, and by which time the patient's often dead. It's not for the care of the individual patient. Same day, and a bit of machine learning on the end, you've got something that you can treat a patient using. here indeed is that infectious disease phenotyping as well, to show where you are on a resistance map, which drugs you don't want to try because your bug's resistant to it. And in my area, as I hope I've given the idea, prescriptions and diagnoses, noisy, categorical data, which have got very high dimension, these are also important. Rolls-Royce, when I was dealing with them, they had exactly the same for their jet engines. They had big old drop-down lists of all the types of things that their jet engines had acquired through time. And machine learning is really good at handling these kind of data. Sensor data, which are often very noisy and artifactual, are very, very well handled by machine learning. And we know a lot about text, of course, and you'll be discussing some of the aspects around the use of natural language processing today, I'm sure. In medical science, there is a ton of free text, but it's obviously got its own semi-controlled vocabulary, and it's got a very, you can't get it wrong. The contents of the thing that you give to the patient to say what was wrong with them, which drugs you need them to take, has to be correct. You're not allowed to hallucinate a recommendation to a patient. So, given this glorious mix of different ingredients in the top row, what do you do with it? So, bottom left was the state of the art 5, 6, 7 years ago. Bayesian non-parametrics. These things are beautiful predictors, handling the noise and the uncertainty in a very principled mathematical way. The joke is, if you're good at maths, you do Bayesian non-parametrics. If you're not good at maths, you do deep learning. So Bayesian non-parametrics is fantastic at handling individual time-varying sequences where there's uncertainty. It's rubbish at being able to handle lots of variables at the same time. Because you've got such a principled understanding of this thing, if you've got a million of those things, it doesn't scale so well. What does scale so well? Generative deep learning is really good at that. So, the building blocks approach we call it graduate student descent. My learned colleague, Andrea Vidaldi, calls it graduate student descent, which is a joke on gradient descent, the manner in which you train machine learning systems. Graduate student descent is getting 100 different graduate students to try different models until one of them works. So that's the unprincipled method of constructing deep learning architectures. You keep tonking around until it works. But for us in medical science, the sweet spot is between these two. So as I showed you on the previous slides, we handle the time-varying models data using these very principled, low-dimensional but rich models, and then you feed the results of those models into deep learning systems. And that's beautiful, because you handle the noise, you handle the uncertainty, you can get rid of outliers, which plagues most applications in my field. But then the deep learning part allows you to fuse all of these different ingredient types and start to learn correlations and interactions and predictive components between them. Haven't really got a huge amount of time left, so I want to touch on this bit on the bottom right, which is meta-learning, machine learning or AI to help us construct models. And what I'm talking about here is, I think I may have an example on the next slide, but one, I'll show you. Suppose, for example, we want to construct a predictor, this fella here, we call it the student. And it's the student's job to do something, predict death, predict which drug's going to work, whatever. And it's doing it from a huge quantity of data. Bog standardly, as I alluded to earlier, you'd step through those data row by row, and you'd keep going until your performance saturated or you run out of time. And that's not optimal if you've got a big complex data set. And it's not optimal if you've got a big complex task. It's not like predicting mortality, yes or no. Maybe it's predicting which bed in the hospital to get ready because this patient's just about to be discharged from the emergency department. That's one of the key settings here. This is published in Europe's year before last. So we have a teacher network to train the student network, and these things learn together. Perhaps that's what happens in real life too, to some extent. So the student is learning to predict mortality or whatever it might be from complex data, and this is reinforcement learning. So the teacher, what is the teacher's doing in a reinforcement learning framework? It has an action, and its action is to choose a spoonful of data from the massive library to give to the student next. The next lesson, the next part of the curriculum. Its reward signal on which the teacher operates is the performance of the student. So if the student's getting better, the teacher knows that that kind of data was working well. And that's what it's learning. It can see the student. Unlike a real teacher, it actually has access to all of the student's brain and can see the synapses, which seems to work quite well. Don't put me in charge of education policy. And the reinforcement learning system works very well here. You get that informative notion. You start to see that the teacher is taking data from the pile that are easy to start with, and the student learns quickly. But then it starts to plateau. And the teacher realizes it needs different data from a different part of the data set to boost performance further and further and further. So a corollary of this is you've assigned informativeness to all of your data. So I can sort my 1 million data points by excitingness or informativeness. Very interesting. So if I want to boost performance a bit more, give me the top decile, please. Don't give me the bottom 90%. Okay, I think in terms of the interest of time, I'm going to skip forward and I'm going to say thank you very much to my army of darkness who do all of the cool research that I've shown you today. And of course, thank you to the funding agencies who provide the lubrication to oil the wheels. Thank you very much. I hope to see you.